You are standing inside a farmhouse in Holmes County, Ohio, at 10 p.m. No fire has burned here since 10 a.m. The last fire lasted 90 minutes, used 2 small logs, and went out on its own. The wall is still warm to the touch. This family pays $0 a year for heat. The stove cost $50 to build. By the end of this video, you will know exactly how to build this system, what every component costs, and whether your property qualifies. In 37 states, this stove cannot be installed on lots under 20 contiguous acres. This is not because of emissions, but because of a certification sticker that cannot legally exist for it. But the reason this system quietly disappeared from American homes has nothing to do with performance, and the business logic behind that disappearance is still costing you money every single month. Each winter, American homeowners pay a steep price to keep their houses warm. Over the course of a typical 30-year mortgage, heating costs alone can add up to anywhere from $42,000 to $72,000. Most families never see this number on a single bill, but the total quietly shapes budgets, choices, and even the way homes are designed. The technology behind these costs often promises high efficiency. Manufacturers advertise lab-tested ratings of 70 or 80%. Yet, in real homes, the numbers tell a different story. Much of the heat produced by a conventional wood stove or furnace never makes it into the living space. Instead, it escapes up the chimney as visible smoke, which is actually usable heat leaving the building. The darker and thicker the smoke, the more energy is wasted. That smoke also carries with it creosote, a sticky tar-like residue that coats chimney walls and dramatically increases the risk of a fire. Despite the familiar hum of the furnace or the glow of a wood stove, the system most people rely on is both expensive and physically wasteful. What's seen as normal is, in fact, a cycle of heat lost, fuel burned, and money spent, year after year. Storing heat in stone is as old as civilization itself. Archaeological digs in the Alps have uncovered Bronze Age homes built around thick stone floors, engineered to soak up fire's warmth and radiate it long after the flames died out. In Germany, the Kachelofens, masonry stoves lined with tiles, became a fixture by the 1700s, prized for their ability to warm a house for a full day on a single firing. The same physical principle appears in the Chinese kang and the Korean ondol, where heated brick or clay channels run beneath sleeping platforms, releasing gentle warmth through the night. Ancient Romans built hypocausts, underground chambers that turned bathhouses into warm refuges in winter, using nothing but fire, stone, and a basic understanding of thermal mass. Yet within a single generation after World War II, this knowledge faded from American life. Factory-made furnaces and steel stoves arrived, marketed as the future of comfort. Modern became a brand, not a principle, and masonry heating slipped from view. The new industry thrived on recurring sales, appliances, fuel deliveries, service contracts, growing to an estimated $30 billion a year. Older methods weren't technically obsolete, just economically invisible. The question now is simple. If the physics never changed, what actually happens inside a machine that claims to revive this lost approach, and can it deliver on its promise? A rocket mass heater starts with a chamber shaped for purpose, not tradition. The J or L configuration forms a right angle between the vertical feed tube and the horizontal burn tunnel. This geometry lets gravity feed small sticks directly into the hottest part of the fire. Instead of logs, it thrives on thin, dry wood, branches, scraps, trimmings, fuel that burns quickly and completely. The system's design encourages a fast, intense combustion, the opposite of the slow, smoldering fires found in conventional stoves. Inside the burn tunnel, fire races through a narrow, insulated path. Temperatures soar, with riser readings often reaching between 1,500 and 1,800 degrees Fahrenheit, according to community builders. The vertical heat riser, heavily insulated, acts as the engine. It pulls in fresh air, accelerates the draft, and produces the signature low roar that gives the heater its name. Here, the fire's energy is concentrated, driving the process forward. At the riser's peak, a transformation occurs. Hot gases, stripped of much of their energy, mix with secondary air and ignite again. This secondary combustion zone is where efficiency peaks. Smoke, unburned fuel in most stoves, becomes flame. Soot and creosote, common byproducts elsewhere, are consumed, leaving exhaust that is mostly water vapor and carbon dioxide. During a proper burn, the chimney releases only a faint shimmer of heat. Instead of sending this heat up and out, the system routes hot gases through a long bench, often 20 feet or more, built from cob, stone, or brick. This is the thermal mass. As gases snake through, they surrender their heat to the dense material. Exhaust temperatures drop sharply, sometimes to just 90 or 100 degrees Fahrenheit, by the time they reach the flue. Most of the fire's energy stays inside the structure, not lost to the sky. The bench acts as a slow-release radiator. After a burn lasting under an hour, the mass remains warm for 12 to 24 hours, radiating gentle heat. The surface never becomes dangerously hot. It is just comfortably warm. Unlike steel stoves, which cool quickly, the thermal mass holds on to warmth long after the fire is out. Material costs are modest. Builders report spending $50 to $100 for essentials: a used steel drum, fire bricks, refractory mortar, and local clay or sand. Many components can be salvaged or sourced secondhand. Labor and time are the main investments. A defining feature is the double reversal snake channel. After leaving the riser, hot gases double back through the mass, winding through a path that extracts every possible bit of heat. Each turn increases contact with the thermal storage, maximizing retention before the exhaust exits. The entire cycle is brief but intense. The fire burns hot and fast, consuming all fuel in under 90 minutes, then rests as the mass radiates stored heat. There is no damper, no attempt to stretch a burn overnight. The logic is simple: store heat quickly, release it slowly. Evans stands out not as a myth maker, but as the first to document what actually happens when a rocket mass heater is used in a real, occupied home. At the Aprovecho Research Center in Coquille, Oregon, Evans measured fuel use in a cottage of the same size, in the same climate, before and after switching from a standard wood stove. The numbers are blunt. Where 4 to 5 cords of wood once vanished each winter, the rocket mass heater ran on about 2/3 of a cord. That is an 80 to 90% drop in wood burned, achieved not in a controlled lab, but in daily life. The promise here is not theoretical. It is measured, witnessed, and recorded in the context that matters most: a home that needs to stay warm through the season. No heating system fits every home or lifestyle, and the rocket mass heater is no exception. Large, open floor plans can leave cold corners, as the system's radiant heat is most effective within a limited range of its bench. Homes that demand constant, even warmth may struggle with the cycle of a single daily burn, especially in regions with extreme cold or unpredictable weather. Some owners find the hands-on nature of feeding sticks, tending a live fire, and managing ash too involved compared to the set-and-forget convenience of a thermostat. Properties without adequate space for a heavy bench, or where code restricts masonry installations, may face practical barriers. Suitability depends not just on the technology, but on the rhythms and needs of the people who live with it. Federal air quality rules for wood heaters are written with the factory in mind, not the workshop or backyard. The EPA certification program, under 40 CFR Part 60, Subpart AAA, requires that every approved stove model be tested as an identical unit, meaning only mass-produced appliances can qualify. For a custom site-built system, there is no path to compliance, because the rules demand a physical test sample that matches every unit sold. The cost to certify a new factory model regularly tops $60,000 in the first year, a figure that dwarfs the entire budget of a do-it-yourself build. Yet, independent testing of a rocket mass heater has measured particulate emissions at 0.12 grams per hour, about 20 times cleaner than the EPA limit for certified stoves. Heavy masonry heaters sometimes qualify for a separate exemption if they weigh over 1,800 pounds, but lighter, site-built designs are left out. The contradiction is structural. The system rewards identical, certifiable products, not the cleanest or most efficient technology. In Jackson County, Oregon, the rules left no room for discretion. In 2022, county officials required a couple to demolish their custom-built heater, a system engineered for cleaner burns and lower emissions than any certified stove on the market. The order was final. Demolition cost $4,200. The replacement, a mass-produced certified stove with higher emissions, added another $9,800. The total was $14,000 out of pocket. This was not a theoretical debate about air quality or engineering. It was a direct financial loss, imposed by regulation, on homeowners who had invested in a cleaner, more efficient solution. Amish families in Holmes County, Ohio, never let the tradition of masonry heating fade. For nearly 2 centuries, their homes have relied on thick, stone-based stoves. These systems store fire's warmth and release it slowly, long after the embers cool. This quiet continuity stands in contrast to the mainstream disappearance of such designs. In 1878, Mark Twain described the German Kachelofens as the best stove ever invented, marveling that one firing could heat a house for an entire day. The knowledge was never truly lost. It lived on in daily use, passed hand to hand, long before the term rocket mass heater was coined. What some call innovation is, in fact, the survival of a principle that never stopped working. Today, families spend over $900 a year on home heat, while a $50 design, tested to emit as little as 0.12 grams of particulates per hour, remains sidelined by code and market inertia. Regulation moves slowly. Innovation waits for no one. Share your story below and subscribe for more investigative breakdowns.